What is TFET structure? Basic operation of TFET structure, comparison between MOSFET and TFET, and the most important, why subthreshold slope of TFET is low. How the TFET performance depends upon the device parameter such as doping, gate work function, gate oxide, and body thickness. I will tell you in brief about tunneling model. I will explain in detail about non-local band-to-band tunneling model. How to write TFET code in Silvaco Atlas, especially how to assign quantum tunneling meshing for planar and non-planar structure. And the last one, different problems occur in conventional TFET and their solution. If you have any query about TFET, please listen this video carefully. You will get all your answer after the presentation. In the previous video, I have talked about subthreshold slope of MOSFET. The formula of the subthreshold slope is this one, ln kT by Q 1 plus CD by CUX. CD is the depletion layer capacitance, CUX is the gate oxide capacitance, kT by Q is the thermal voltage. From this formula, you can observe that the subthreshold slope of MOSFET is always greater than the 60 mV per decade. It cannot be less than 60 mV per decade in case of MOSFET at room temperature, because depletion layer capacitance is always greater than or equal to oxide capacitance. The lowest possible value of subthreshold slope for a MOSFET is 60 mV per decade at room temperature. For example, to get an I-on by I-off ratio 10 raised to power 5, we need to apply a gate voltage 5 into 60 mV into M is equal to 0.3 volt. This means for change in 1 decade current, we need 60 mV voltage. To produce 5 decade change in current, we have to require minimum voltage 0.3 volt. Therefore, it is difficult to scale down the supply voltage if we want to raise a large I-on by I-off ratio. To overcome this fundamental problem of poor subthreshold slope and large off current of the MOSFET, an alternative device was necessary. One such device is the TFET, tunneling field effect transistor. Structure of TFET is different from the MOSFET because it has asymmetrical structure, whereas MOSFET has a symmetrical structure. In case of MOSFET, the source and drain region have same material, but in case of TFET, the source has different material than drain material. Distinct performance in terms of speed, power dissipation, and subthreshold slope lead to emergence of tunnel FET as a potential substitute for several gate engineering MOSFET. TFET is defined as a semiconductor device in which gate controls the source drain current through modulation of band-to-band tunneling mechanism. TFET can exhibit subthreshold slope below 60 mV per decade due to a fundamental difference in the mechanism of current control as compared to MOSFET. In MOSFET, the current depends upon the harmonic emission of free charge carrier that will move across the potential barrier. But in case of TFET, the current mechanism depends upon the band-to-band tunneling mechanism, in which the electron make a tunnel between the depletion layer and move from source to channel region. In MOSFET, the free charge carrier move over the barrier to reach a drain region, but in case of TFET, it will make a tunnel between the barrier to reach at the drain region. There are two equations are given below. First one is the harmonic current of in MOSFET, and second one is the band-to-band tunneling mechanism in TFET, in which A and B are material dependent parameter. It will depend upon the material characteristics, doping, etc. As you can observe that the potential barrier at the source channel junction is very wide in the off state of the device when VGS is equal to 0 volt and VDS is equal to supply voltage is equal to 1 volt. So that TFET exhibit very low off state current because of the large depletion layer at the source channel junction. As we increase the gate voltage, the energy band in the channel moving downwards and the barrier width at the source channel junction is reducing. At a certain voltage of VGS, that is threshold voltage, the valence band of the source get aligned with the connection band of the channel. Then electron can make a tunnel from source to drain region, and now the transistor is in on state. Apart from the limitation imposed by the subthreshold slope, MOSFET in less than 50 nanometer channel region suffer from various show channel effect such as DI-bell, high threshold voltage, etc. Due to band-to-band turning mechanism and asymmetrical structure of TFET, TFET have great immunity to these show channel effects and its ability to work on subthreshold and super subthreshold voltage. It is also independent of geometrical scaling and produce high on by IO ratio. There is one disadvantage of TFET is that it has low on current. But by using the various technique, we can increase the on current of TFET. Now, the most important part is why subthreshold slope of TFET is low. In subthreshold region, a MOSFET conducts current by the mechanism of diffusion of carrier across the channel and can be written by this formula. You can note down. The subthreshold swing of the MOSFET is defined as the d log IDS by dVGS. Hence, the subthreshold slope of MOSFET is constant with VGS. On the other hand, TFET, even in the subthreshold region, current conducted by the mechanism of band-to-band turning by this formula. As seen in the above equation, the turning generation rate is an inverse exponential function of the electric field, which is in turn as a function of VGS. Band-to-band generation rate is inversely proportional to the electric field, so that the subthreshold slope is vary with the gate voltage and does not have a constant value as in the case of MOSFET, because electric field is dependent upon the gate voltage. Hence, for a TFET, two kinds of subthreshold slope are defined in general: point subthreshold swing and the average subthreshold swing. The point subthreshold swing is defined by the same formula as we have calculated in the case of MOSFET. But in case of TFET, we can also calculate the subthreshold swing by another formula in which VGS is varied. The average subthreshold swing is defined over a range of VGS value by this formula, in which VTH is the threshold voltage of the TFET and VOF is the gate voltage at which the drain current begins to increase rapidly. IDS VTH is the drain current when VGS is equal to VTH. IDS VOF is the drain current at VGS is equal to VOF. The threshold voltage can be defined as the gate voltage at which the drain current reaches to 10⁻⁻⁷ at VDS is equal to VDD, where VDD is the supply voltage. Performance dependence on device parameter. As you can observe in the figure, a higher doping in the source side, that is Na1 is greater than Na2, leads to a shorter depression region at source channel junction. Due to this, as indicated in the figure, the electron occupying the valence band edge in the source would have to tunnel through a shorter distance in case of higher doping as compared to larger distance in case of a lower doping. Therefore, the turning probability would be greater in case of higher source doping, thereby reducing in a large on-state current, thereby resulting in a large on-state current. Following a similar reasoning, an increase in the drain side doping would lead to a greater drain channel tunneling in the case of negative gate bias, thereby increasing the ambipolar current. In many applications, the ambipolar current need to be minimized, which may be accomplished by reducing the drain doping. This is the drain current characteristics only for the drain doping, not for the source doping. For the source doping, we have make energy band diagram. If you are increasing source side doping, the depression layer distance gets reduced and the current gets increased. Next is the gate work function. In this figure, I have compared the band diagram of TFET with a higher gate work function phi C1 to that of TFET with a lower gate work function phi C2 at thermal equilibrium. Due to the formation of a great inversion charge layer, in case of higher gate work function, the energy band of the channel are lower. This leads to a steeper source channel junction, thereby increasing the source channel tunneling and the on-state current. The increase in on-state current is accompanied by an increase in the off-state current and thus an increase in the power dissipation in the off-state. This is the band diagram along the surface of N channel for different value of the gate work function. This is the transfer characteristic curve of N channel TFET with different value of gate work function. Another effect of changing gate work function on the transfer characteristics can be seen in the figure B, shifting of the center point of the curve value to the left upon by decreasing the gate work function. If you are decreasing the gate work function, curve starts shifting on the left hand side. Decreasing the gate work function, increasing the source channel tunneling and decreases the drain channel tunneling, which would raising the right hand side curve and lowering the left curve along the current axis, thereby shifting the center point of the curve to the left. There are two functions of the gate oxide. First one to insulate the gate and the second one to enable the gate to control the electrostatic in the channel. Since the oxide is an insulator, the gate oxide prevents current leakage from the channel to gate. The oxide capacitance is given by Qx is equal to epsilon Ox divided by Tux, where epsilon Ox is the permittivity of the oxide and Tux is the thickness of the oxide material. As the formula of the oxide capacitance shows, the gate oxide capacitance can be increased by reducing the thickness. A greater oxide capacitance leads to a higher charge being formed in the channel at the same gate voltage, leading to a great control of the gate on the electrostatic of the channel. However, a thinner gate oxide material may lead to some carrier from the channel turning to the gate, generating a leakage current, which is most undesirable. This can be prevented by use of a material with high permittivity, such as HFO2 oxide in case of SiO2. We cannot use HFO2 is direct. We are using with the gate stacking, in which we are using the SiO2 plus HFO2 as the oxide material. By using the gate stacking, this would cause a thicker potential barrier between the channel and the gate, as the use of gate stacking SiO2 plus HFO2 has added the benefit of further reducing the oxide capacitance and increasing the gate control of the channel. The most important point to understand, in case of SiO2, we cannot reduce the oxide material to a large extent because it will increase the leakage current. By changing the SiO2 into the gate stacking SiO2 plus HFO2 will increase the oxide thickness by using EOT formula, equivalent oxide thickness. Next is the body thickness. The impact of the silicon body thickness on the drain current depends upon two competing effects. As the silicon body thickness increases, the volume of silicon available for band-to-band tunneling is also increases, thereby increasing the drain current. But as the thickness of the silicon body increases, the coupling of the gate with the channel degrades, leading to a decrease in the drain current. As a result, only an optimum body thickness TFET can maximize the drain current. For the double gate TFET, the drain current reaches maximum when the silicon body thickness is between 10 to 20 nanometer. In the literature survey, it is also found that the subthreshold swing is strongly dependent on the thickness of the TFET body. As the thickness of the body is reduced, the subthreshold swing of the TFET improves. Next is the tunneling model. There are different tunneling models available in TCAD with different degree of accuracy and computational resource requirements. First one is the local band-to-band tunneling model and the second one is non-local band-to-band tunneling model. The local band-to-band tunneling model is further divided into standard model, snack B2B model, cane model. Standard model is further divided into standard B2B model, Calcine B2B model and the Harex B2B model. Their syntax and command is given below. For snack B2B model, bbt.snack is used, bbt.cane is used, bbt.std is used, bbt.kl is used, bbt.harex is used. For non-local model, we have used bbt.non-local command. In local band-to-band tunneling model, when electric field inside a device is high enough, then there is a sufficient bending of bands such that the turning of electron from valence band to the conduction band is started. In local band-to-band model, the turning probability is calculated by assuming constant electric field in the depression layer. In this presentation, we will talk about in detail non-local band-to-band model. The turning current in forward and reverse direction for a degenerate PN junction can be successfully modeled using non-local band-to-band turning model. The turning mechanism is only applied to the degenerate PN junctions. The degenerated PN junction are used in TFET structure. For understanding about this degenerated PN injection model, you can do Google. To enable this non-local band-to-band model, we have used bbt.nonlocal command. bbt.nonlocal has to be specified in the model statement. Along with the specification of bbt.nonlocal parameter in the model statement, a mesh, quantum tunneling mesh, has to be defined in the area containing a single PN junction where quantum tunneling is expected. The quantum tunneling mesh consists of series of parallel 1D slices along which tunneling takes place, and each slice is approximately perpendicular to the PN junction. Atlas has two methods of setting up these area of slices. The first method is only applicable to planar junction parallel to the x or y axis. It allows you to set up a rectangular area using the q2x dot mesh and q2y dot mesh statement. You can also specify the number of tunneling slices and the number of mesh points along the slice. Atlas has two methods of setting up these area of slices. The first method is only applicable to the planar junction parallel to the x or y axis. It allows you to set up a rectangular area using the q2x dot mesh and q2y dot mesh statement. You can also specify the number of tunneling slices and the number of mesh points along the slice. In this example, we are using the two q2x mesh statement in x direction and two commands in y direction. This statement will set up an area bounded by the sides. By additional setting the qtnn.dir parameter on the model statement to be 0, you define the turning direction to be y direction. If the turning direction is in the x direction, then set qtnn.dir to 1 on the model statement. It is recommended to have an fine mesh as possible in the tunneling direction, both for the physical mesh and the tunneling mesh. Next in the figure, you can observe this quantum tunneling meshing region from 35 nanometer to 65 nanometer with 5 nanometer spacing. You can note down that from 35 nanometer to 65 nanometer in x direction, the spacing is 5 nanometer, and in the y direction, from 0 to 10 nanometer, the spacing is 2 nanometer. So that the total lines are 6 in y direction. The second method of setting up a mesh for tunneling can be applied to either planar or non-planar junction. To use the second method, create one or more QT region statements. This statement must be located after the meshing electron and region statement but before the model statement that specify bbt.nonlocal. Single or multiple quantum tunneling meshes can be defined in this method. If direction of the tunneling is not along one direction, that is neither parallel to x-axis nor y-axis. To define quantum tunneling meshes in the method 2 statement with the help of QT region statement, the positional coordinate of 4 corners 1, 2, 3, 4 of quadrature must be specified in the anti-clockwise direction. You can see in the figure, we have selected these two 4 corner 1, 2, 3, 4 in anti-clockwise direction. The positional parameter of point 1, 2, 3, 4 are given by the real parameter x1y1, x2y2, x3y3 and x4y4 in pairs. The distance between slices on the side of the junction on which point 1 and 2 lie can be specified by the value of real parameter snrm.beg and on the other side of the junction by real parameter snrm.end statement. The value of snrm.beg is 6 nanometer and the value of snrm.end is 2 nanometer, which means spacing at the point 1 and 2 lies is 0.6 nanometer, and on the other side of the PN junction where the point 3 and 4 is lie, the spacing is 2 nanometer. This means snrm.beginning and .end simply specify the spacing at two sides of the junction. Similarly, the spacing between the mesh point or nodes at the beginning and end of the slice can be specified by the real parameter stnl.beg and stnl.end. In this statement, the value of this STNL dot beginning and STNL dot ending is 5 nanometer. It is representing the spacing in the x direction. The value of STNL beginning and end is same, so we get the same spacing from point 2 to point 3, that is 5 nanometer. This is the first QT region statement from different coordinate of the rectangular axis x1 y1, x2 y2, x3 y3 and x4 y4 with y direction spacing from one side of the junction to other side of the junction, and STNL dot end is x direction spacing from one side of the junction to the other side of the junction. If the structure is non-planar, then we can use number of QT region statement 1, 2, 3, 4 and make number of rectangular coordinate. This is for the planar junction. For non-planar junction, you have to make number of QT region statement. We will discuss about the non-planar junction in the next slide. For tunneling through non-planar junction, it is preferred to construct a complicated polygon region to use the PBT non-local method. One more important point to know that to calibrate the BBT non-local model, you can specify the value of the effective mass. Set the value of the effective mass, we will use ME dot tunnel and MS dot tunnel on the material statement. If ME dot tunnel and MS dot tunnel is not specified, then the value of specified MV, that is conduction band effective mass, valence band effective mass on the material statement is used. The turning current is more sensitive to effective mass because the turning probability depends exponentially on them. Across very high top junction, the band-to-band turning current can be very high and depends very strongly on the band edge profile throughout the junction. In turn, the injected turner current creates a charged dipole and strongly affects the potential and consequently the band energies at the near the junction. This strong coupling can pose convergence problem in some situation. Atlas has two features to try to migrate this problem. First, you have to specify BBT.NLD-ERIBS on the model statement to include non-local coupling. Second, the position at which the turner current is injected into the simulation can affect convergence. As an alternative, use the parameter BBT.forward on the model statement. This causes the turner current to be injected at the start and end position of each turner slice. The parameter BBT.reverse on the model statement causes the turner current to be injected in locally charged neutral manner across the width of the junction, thus avoiding the creation of charged dipole. This is the device parameter and cross-section view of a double gate TFET which are simulated using Silvaco TCAD tool. Please note down. The source doping is 10 raised to power 20, drain doping 5 into 10 raised to power 18, channel doping 10 raised to power 17, channel length 30 nanometer, drain length 100 nanometer, source length 100 nanometer, gate oxide thickness 3 nanometer, silicon body thickness 10 nanometer, gate work function 4.5 electron volt. The important point to note down that in case of MOSFET, we cannot reduce the channel length less than 50 nanometer because show channel effect increases which results in the large leakage current. But in case of TFET, due to asymmetrical structure and band-to-band turning mechanism, I have reduced the channel length up to 30 nanometer. Let's go for the code. Start from Atlas. First one is the meshing. Meshing should be fine as fine as possible, especially at the junction point, mainly at the turning region source channel interface. You can also copy the double gate TFET code and run on your PC. X-axis meshing is varying from 0 to 30 nanometer and the Y-axis meshing vary from minus 3 nanometer to 30 nanometer. You can see the variation in spacing at junction meshing is fine, and at other points I have taken post meshing. After that, I had mentioned region number with material 1 and 2 and 3. After that, I have defined electrode statement. gate, drain, source and gate 2. Note that the channel length is 30 nanometer. After that, defining meshing for non-local band-to-band tunneling using method 1. This one. We are using 3 statements for the X meshing and 3 statements for the Y meshing. In the X direction, the QTS mix is defined for the 50 to 200 nanometer, and in the Y direction, it is defined for 0 to 10 nanometer. In another code, I have defined the QT meshing using method 2 for planar and non-planar junction, in which we are using the 3 QT region statement with points tunnel, with rectangular coordinate x1, y1, x2, y2, x3, y3 and x4, y4 with SNRM at the beginning. This means spacing between mesh point on the nodes at the beginning, and SNM.end is the spacing between the mesh point on the nodes at ending of the slice. You can use any quantum tunneling method for defining the mesh. We will get approximate result for the planar junction, but non-planar junction you have to use method 2, that is more effective. Let's go to the previous code. Next, I have defined the material statement for assigning the effective mass of electron. The turning current is most sensitive to effective mass of an electron in silicon material because turning probability depends exponentially on them. After you have to define different doping of source, channel and drain region, the doping profile is assumed to be a abrupt profile. Next, you have to define contact for the different region, gate, source and drain. Next, you have to assign the model used in the TFET. After that, apply voltages with the help of the solve statement. The drain voltage is increased gradually to avoid convergence problem. After that, you have to save the structure file and log file and observe it using Tony plot command. Last one is equate. When you run the program, you will find 2 files. One is the structure file and one is the log file. This one is the log file and this one is the structure file. You can extract the data from the log file using export command, and data from the structure file, first you have to save it in that format. After that, you can extract the data in the CSV format. For more understanding how to extract data from the log and the structure file, please watch my previous video. Last one, there is some problem in the conventional TFET. First one, the major problem is abrupt junction is required in TFET. Last one is some problem in the TFET. First one is the abrupt junction is required in TFET. Second one, required costly doping technique such as diffusion and the ion implantation. During diffusion and the ion implantation, some atoms are dislocated from the original position, so that high temperature process such as temperature annealing is required to move the atom into the original position. By applying this high temperature technique, thermal budget of the device is so high, so that we are switching from junctionless and the dopingless TFET. Dopingless TFET, you can also say that charged plasma TFET. My dear friend, this is the end for today. Please like and subscribe my channel. Thank you.